Hi, my name is Steven. Together with my colleague Ben, we're going to talk to you about how we're using a content-addressable storage in Clang for caching computations and eliminating redundancies. First of all, what is our vision? Our observation is that compilers are getting more and more complex. You use lots of resources like computations, memories, and storage, but much of the work it does is actually redundant, like parsing the same source file or optimizing the same function. Our solution to this problem is using a content-addressable storage, also known as a CAS. Back in February, Duncan posted this RFC to the LLVM discourse proposing integrating CAS into LLVM project. We got a lot of good feedbacks, and a lot of people expressed interest in this new development. Today, we're going to update you with our latest status and hope to inspire more people to join us in this new technology. What is our agenda today? First, we're going to talk to you what is CAS and our CAS proposal. Then, we're going to go through some of our prototypes, including Clang caching and CAS object files. In the end, we're going to talk to you some about potentials and future works that can be enabled with a CAS inside LLVM. For those people who are not familiar, CAS or content-addressable storage is a technology where the content is stored is going to be assigned a unique address based on its content. It's widely used in many domains. Actually, inside build systems, a lot of build systems utilize underlying CAS to optimize build tasks, but it's a fairly new concept to be introduced inside the compiler. There are many benefits to have a storage system like CAS, but two of the main characteristics we're trying to take advantage of is its data uniqueness and immutability. Compared to a traditional storage system like a file system, where you can store the same content into different file paths, with a CAS, it's guaranteed that the same content will be associated with only one address, saving storage space and, more importantly, expose redundancy automatically. The data immutability means the data associated with one CAS address cannot be modified. If you modify any data, it will result into a different CAS address, which is not the case, again, with file system. This is a very important property that we use to build caching system, and we hope to show you why later in more examples. Now, let's talk about our proposal and our proposed CAS library. The libcas we propose has two main components. The first part of it is a collection of CAS APIs. They're designed to be easy to use for compiler integration and can also be extended to use different CAS implementations, like a remote CAS. It has an object store class, which is the interface you use to load and store objects from a CAS, and also an action cache class, which is a key value storage, which you can use to associate inputs and outputs of computations if you can express them inside a CAS context. The second part of the library is what we call a built-in CAS. It's a default CAS implementation we decided to put into LLVM. It's simple, but yet performant enough for production usages. Unfortunately, today we don't have time to show you the detailed design and trade-offs we took to design the built-in CAS, but if you want to know more later, feel free to talk to us. The basic unit in our CAS library is what we call a CAS object. The CAS object have two main components. The first part is a data blob, which is you can use to store arbitrary data. The second part is a list of refs, where you can use pointing to other CAS objects. When you compute the address of the CAS objects, you need to consider both data and ref, so that, for example, two CAS objects with identical data blobs and two different lists of refs are considered two completely different objects and have different addresses. With this model in mind, we can build graphs out of CAS objects. You can build graphs bottom up from the leaf nodes, and the property of the CAS guarantee that there cannot be any cycles. Thus, it's going to all be direct acyclic graph. You can also easily composing big CAS object graph from smaller ones. You can also easily infer the equality of CAS graph by just comparing the address of the root nodes. One abstraction level above the CAS object is what we call CAS schema. You can think that as a model we use to serialize and deserialize high-level objects from CAS. Here's a simple example. On the left, there's a file system tree where there's some directories and files, and some files share the same content. We develop a cache file system schema that can convert the file system tree on the left into a cache graph on the right. But more importantly, on the other side, if a consumer who knows about cache file system schema can take the cache graph on the right and traverse that as if it's a file system on the left. With the basic of the cache out of the way, let me hand it to Ben to tell you more about Clang caching.
Talk about how we use the cache libraries that Stephen talked about to add caching support to Clang. The motivation here is that our compilers are doing redundant work. This can happen both within individual builds, such as repeatedly accessing the same headers, as well as across subsequent builds. For example, locally, you might change branches and then change back and need to rebuild the same sources. Or in a CI system, you can imagine us doing repeated clean builds of very similar sources. We'd like to be able to cache these computations, but unfortunately, the inputs are not always well specified in the compiler. And we get these inputs from a mutable source, which is the file system. Our solution to this is to use a persistent cache and build against it. This allows us to isolate the pure computations from the compilation from the mutable file system. This gives us a sound and efficient basis for doing caching that's correct by design. I'm going to go through the example of compilation caching. What do I mean by that? So this is caching at the translation unit level in Clang. You can think of this as similar to Ccache, but done using compiler integration. Using compiler integration allows us to do it more soundly and more efficiently, as well as to be able to support Clang modules. We've implemented this support in our experimental cache branch on GitHub. Let's take a quick look at what a cached compilation can look like. We have a simple CPP file that's including a header. When we go to compile this file, we're going to add our new caching launcher. I've also added a remark flag so that we can see what's going on with the cache. The first time we compile the file, as we would expect, we're going to get a cache miss. We're also printing out this cache identifier. This is a representation of all of the inputs that went into this compilation. This is also the cache key that we're going to use when we access the action cache to look for results. The second time we compile the file, of course, we get the same inputs, and so we get a cache hit. We can now replay the objects and other results directly from the action cache. So how does this all work under the hood? Well, first, Clang scandeps is being used to discover the inputs of the compilation, and we're ingesting those into the cache. Second, we're producing a new CC1 Clang invocation that's only going to have access to the cache. Finally, we capture the outputs, and at this point, we can fearlessly cache the results because we now have immutable inputs and immutable outputs. Let's talk a little bit about input discovery. I said that we use Clang scandeps. Well, for the purposes of this talk, the important thing is that Clang scandeps is a compiler-based library that allows us to discover both file and module dependencies of a translation unit. And it can do so much faster than pre-processing. I don't have time to talk about how Clang scandep works, but for more information, I've linked a couple of previous talks that have been given at LLVM Dev. They go into lots of details about how Clang scandeps works and also how it's used in explicit modules builds. So as we use Clang scandeps and discover inputs, we still need to ingest those into the cache. And one way we can do this is using something called caching on disk file system. This is a new VFS implementation for LLVM that allows us to ingest files. So how does caching on disk file system work? Well, we use this as the base VFS layer in Clang, and then we keep track of every single file system access that's made during the Clang scandep scan. So for example, we might start by opening the main CPP file, we might stat a directory for a header include path, et cetera, et cetera. Also, as we're tracking these accesses, when we see a file, we immediately ingest its contents into the cache. This ensures that the contents cannot change across the scan or in the later compilation. Finally, once we've finished scanning an entire translation unit, we can build a CAS file system tree similar to the one that Stephen showed earlier. At the leaves of the tree, we have the files that we already ingested, and then we can create CAS objects for all of the directories with references pointing to all of their contents. At the root of this tree, we have an object that represents the entire CAS file system that was accessed as part of this scan. We can then pass this back into our modified Clang CC1 invocation with the new fcasfs option. And at this point, we have all the pieces we need to do a cache key. We have a modified CC1 command that uses CAS inputs. We have the CAS file system itself, and we have some notion of the compiler's identity or version. Indeed, if we go back to our previous example and we print out what the CAS actually contains for this identifier, it has exactly that structure. We first have the command line invocation that's been modified to access its inputs through the CAS. We have the CAS file system, and it includes all of the files that we would expect as part of compiling this file. So caching on disk file system is actually a fairly general tool and can be used to add caching to other places. We've used it as part of an experiment for caching in LLVM table gen. But for Clang specifically, it leaves some room for improvement. First, it's conservatively modeling all of the file system accesses. This can have a level of detail that's unnecessary in some cases, which adds overhead. Second, and more importantly, there are certain kinds of dependencies that can become too coarse-grained in this model. For example, header map files and virtual file system overlay files often contain a list of all of the headers that are included in an entire project or target. You can imagine that we might add a new header, and then it causes cache misses across a wide space, even though nothing is actually including it yet. Our solution to this is something we're calling include tree. This is a domain-specific cache data structure we're using, and it allows us to save at every include location which file is being included. In this model, the header search only has to be run during the dependency scanning phase. When we come to later do the cached compilation, we can replay those include directives directly from the data structure. This means that our cached compilation no longer needs to reason about search paths, header maps, virtual file system overlays, etc. As a quick example of what an include tree looks like, if we have a CPP file and some headers that include each other, when we compile this file with include tree enabled, the cache key that we looked at earlier has been changed, and now we have a CAS include tree that's being used in place of the CAS file system. As its name suggests, the include tree has a tree structure. It starts with the main input file. We have a CAS reference that points to its contents, and then for every source location in that file, we have a reference to an include tree for that included file, and so on recursively. This has been a quick tour of how we've implemented caching in Clang. But let's take a look at what it looks like when we use it to build a real project. For example, if we're building Clang itself, we can add the new cache launcher to our CMake invocation. Then, the first time we build Clang in the that hasn't been cached yet, let's say it took about 9.5 minutes on the machine that I ran it on. If we come back later and need to recompile the sources, I'm cleaning here, but you can imagine switching branches or switching back. We can now replay this build in only 17.5 seconds. Let's take a look at how those numbers compare. So first, if we compare to a baseline compiler that has no caching support enabled, you can see we've added only a few seconds to that first uncached build. Now, we have ideas about how to eliminate all of this overhead, but we're already doing well compared to other caching tools like Ccache. Things look even better when we look at the fully cached rebuild case. Our 17.5 seconds is significantly faster than the other tools. A quick summary of the compilation caching that I talked about is that we've added caching support to our experimental CAS branch of Clang. Doing this with compiler integration allows us to do it more efficiently and more soundly. We're using fast dependency scanning from Clang scandebs. We're getting isolation from the mutable file system using the CAS, and we're building domain-specific cache data structures, such as include tree, to improve the work. All of this is designed to be able to work with Clang modules, which is something we're continuing to work on. Now, compilation caching at the level of translation units is only one kind of caching that's possible, and at the end of the talk, we'll circle back to some other opportunities in this area. But first, I'd like to bring Stephen back up to talk about CAS object files.
Thanks, Ben. CAS object file is another prototype we built to showcase how powerful a CAS can be when it comes to optimizing builds. As we all know, build artifacts are large. They're expensive to store, and it can be a bottleneck when it comes to building an object cache. But there's a lot of information within the object files that are duplicated, both within a build and across a build. Within a build, you can find duplicated information in data like strings, ODR functions like C++ templates, or a lot of part of debug information. Across the build, let's look at an example where there's an object file with a lot of functions. If we go ahead, just update one function, the resulting object has very limited changes, but it's kind of scattered all over the place. It not only touches the function you change, also affecting lots of addresses and relocations. But with the bulk of the object file still unchanged, it will be really good that we don't need to store those content multiple times. So we built what we call a CAS object file format, which is a scheme we use to store macro object file inside the CAS. We write a new object writer inside MC that can directly write macro object into CAS objects. It utilizes all the machine code information like MC fragments to break up object files into blocks that can be reused later. It's also a lossless format, which means you can serialize that back into a macro object file and compare it for verification. To test how good this new format performs, we just built LLVM project. We took one commit per day from the branching point of LLVM 15 and see how much object storage cost do we need across a 10-day period. And what you see here is the storage cost using native objects. When we store release build artifacts, and we already dedupe all the object files so that unchanged object file only gets stored once. Now let's take a look at if we use a CAS optimized object format. You can easily spot that we have space saving all across the board. But more importantly, when you use a CAS object file format we developed, you see a much slower growth rate in the storage cost, only 66% for 10 builds comparing to using native object, which has an increase of 259%, setting up a significant long-term benefit. Now, let's look at an optimized build with debug information. With debug information, you was expected that it's going to use a lot more storage and have a steeper growth rate. But we can see the same trends holds for the CAS object files. It really shows that CAS object format has a real-world potential for all kinds of build configurations. Now, let's talk about future. Other than the work and prototypes we built already, there's much more we can do. One of the most important ones is we want to explore opportunities to enable finer grained caching that can expose more redundancies in our decompilation tasks. We have a working prototype of a Clang token cache, which is a finer grained compilation cache than the whole module one we just described above. But I think we can do more. For the long term, we discuss the opportunities that we can refactor Clang into a request-driven model so that it can be more cache-friendly. We also briefly mentioned debug information. There's more we can do to optimize debug information. For example, we can change layout of the line tables or type infos so that it can be more cache-friendly. As we mentioned before, we also build caching capabilities into a lot of other build tools like LLVM table gens and linkers. We also have people express interest to express other kind of build artifact in a more cache-friendly way, so we can optimize them as well for size and speed. In the end, I'd like to remind you again for all the places that you can learn more about this new technology. You can always read our initial RFC thread, which shown on the slides above. And we're going to hold a roundtable later today, and everyone is invited. All our examples and prototypes can be found on our GitHub branches, and we already started working to upstream some of them. There are 2 pull requests shown on the slides, both of them coming with a stack of changes, and we have many more queue up after that. We're really excited to get cast upstream so it can benefit your application as well. Thank you. Ben?
There's 2 microphones for question.
Questions?
Yeah, really nice work.
Thank you.
Just as a side remark, I think thin LTO already has a caching layer too, which might be pretty easy to plug in. And then one question, usually I need to manage my storage at some point. What if I want to take 20 gigabyte of my hard drive and want the object cache to not grow any larger? Is there any support to do that?
Yes, so let me answer, there's 2 questions. The first part is, how about thin LTO, right? So thin LTO already have a cache, but you can think that it's a pretty easy system that we can plug in here because it kind of compute a cache and also have, kind of the key value storage can fetch the output. We have a prototype that showcased that too, but it's a much harder thing to show that's a pure computation without, you can verify the thin LTO hash computation is like a pure computation that we can confidently cache in a global space like Clang caching, but that's definitely something we're gonna explore more. For the cache design, you're mentioned about how do we manage the size and et cetera. That's part of the thing that I mentioned about the building cache design and the trade-offs we took. For the current prototype, we don't have anything to manage the lifetime or purging caches, but we do have ideas how to improve or limit size. And it's also some kind of trade-off we're gonna prioritize, but that's definitely a good input. Thank you. Yeah.
So 17 seconds from 9 minutes is a great optimization for compiling Clang. What is taking 17 seconds?
So table gen is actually a non-trivial part of the compilation. The build I showed with 17 seconds was a release asserts build. If you look at debug, it's kind of the same pattern, but with bigger base case because of table gen. And we actually have a prototype for caching table gen as well that helps with that. Linking is obviously important there. That's even more important the more binaries you have, or if you have LTO involved. And then, of course, the way that the caching is done at a low level can have some overhead if you're having to replay a lot of I/O. Now, it's pretty efficient already, but you could imagine sort of layering this with caching and other layers to be able to cache, to discover that you have all the inputs to the linker, and if the linker is also caching and it has the results already, maybe you don't need to do that I/O at all. So.
Thanks.
How do you handle PGO builds, like when you have, in addition, data flow and other things? Does your scheme handle PGO both, for example? Not both, of course not, but PGO. Profile-based optimization on Clang.
Yeah, we haven't tested that, but you can easily think that you can take PGO inputs, which is whatever the profile generated as part of the input. So I don't think it's currently captured in that files on this include tree, but we can definitely we can definitely change our cache modeling to include any kind of inputs. But on the other side, you can always have a trade-off. I don't think PGO data is the case. But if you just constantly regenerate PGO data every single run, it's gonna be generating a source of things that are gonna change cache key every single time, which will impact your cache performance for sure.
It's also a place where a finer-grained caching could help in the future because the PGO comes in later in the pipeline. So there's potentially things we could be caching that would not be affected by it as well.
Yeah.
I wanted to follow up on the 17-second question and what happens on a perfect cache hit rebuild. So I assume every time Ninja will reinvoke Clang, you have to rerun the scandep tool.
Yes.
And something that may be complicated is you have to revisit every include folder because during the include resolution, every folder that doesn't hit could hit on the rerun, right?
That's right.
To find a header. And so that's a lot of hits to the file system actually, right? In the other things you have thought of to optimize this as well?
So there's very limited we can do inside compiler for file system access, but like we can definitely imagine the world that if we can have more caching and cache support. For example, if your entire file system is based on a cache, then all you're doing is sending cache requests. Then you don't need to re-ingest all the file because it's already in the cache. So that's kind of the perfect world if you can imagine one. You can definitely cut down all those costs for visiting the file and computing their hashes, ingest them into a cache in the first place. That can be all happen in advance if your entire inputs is already in the cache.
I guess another note there is that we're not running the scanner with like a separate file system for every compilation. We use a single scanning instance, so it can cache the file system accesses and ingestions.
So you keep a process running during the entire compilation flow? Like there's a background server running or something?
Yeah, we
Yes.
didn't have time to get into like that architecture, but like we have a couple modes. Either we can sort of implicitly launch something for you if you want like a sort of drop-in, or if your build system is willing to adapt to using like some of our APIs, it can be done explicitly as well.
Yeah, that makes sense. Thank you.
Hi, quick question. From what I understand, you're using local cache. Basically, if you build your project that's stored on your local disk, have you considered doing a distributed cache? This way, if you have hundreds of people on your team and everybody building, same version of compiler, same version of source, everybody could take advantage of one person doing the build and everybody using the cache from, after first person populated the cache, everybody using the results. So we just did a similar project in Sony like a week ago. So I was wondering if you ever considered that.
Yeah, so if you're looking at the prototype we built, we already have that functionality. So there's two parts of that thing. One is we can definitely have a remote service, can implement a cache. We definitely want to work with community to see what's a good protocol or interface. We can talk with a remote caching service that we can have different implementations. That's definitely one of our goal to bring up here, so that we can store object file and all the other build artifacts remotely, and we can fetch it. So we already have that capability in our prototype. We just don't have time to get into that today. The other part of that is you can see that we still not fully disconnect from the file system. So if you with the current model we designed in the talk, you kind of need to have all the sources and build directory in the same places for everybody before you can get a perfect hit. But we also have a different technology that we can remap all the files into canonical locations, so that no matter where you put your source or where your build directory is, you can get almost perfect cache.
But that if you just have some shared space, it comes with a lot of problem, for synchronization, and all other kind of things that when several people could write at the same time in the same place. So maybe we were actually using a database, so which takes care of all these issues. So is it something that you want to consider, or you just want to take care yourself of all the synchronization and all that stuff like that?
We definitely want to talk to more people to see how their system works. So we really want to work with community to working out a solution that can benefit lots of people. And definitely I'm interested to know how Sony use your caching system and how do you solve all different problems, so we can make sure whatever we design here can work for you as well.
Okay, thank you.
Yeah, no problem.
All right. Let's thank Stephen and Ben for the presentation.
Thank you.